Okay, this is Paul Gregg, and I'm going to talk about it's kind of a design review of the Little Rocket roller coaster. This is actually out of sequence. This is the third roller coaster I made. I'll talk about the second one, the larger one, at a later time. But so this is the little roller coaster I built for the smaller kids. But it's probably the highest quality one with the most experience and thought put into it. So this is kind of why I'm doing this. It's just kind of for fun, and the kids like it. So I somehow this is out of control, but we have to have fun. So this is kind of the design requirements and objectives. It's intended for small children, maybe up to 60 pounds. I think I lowered that to 30 pounds later. Factor safety 1.5. Keep the G's under 2 and under 10 miles an hour for the speed. 14-inch rail gauge, distance between the two tracks, center to center. And I decided to try out the Ackerman steering. If you want to know the difference between Ackerman and bogie steering, there's a good Wikipedia article on it, and you can go to that. I won't explain it all. But basically, the bogie steering system is like the two left and right wheel sets are connected by a cross member which spins. Um, that cross member, every time it spins back and forth, it takes some energy out of the system, but it works really well. Um, and that's how most roller coasters are made, and my other roller coasters are made that way. But this Ackerman is more like a car steering, where each wheel pivots independently, and there's maybe a small bar that hooks them together so they track parallel. So I thought that was very interesting. Um, but when you're in a corner, it kind of the apparent distance between the wheels changes, and so I went ahead and have a different width of the track in the turns as opposed to the straight parts. And I'll explain that later. 22-inch distance between the fore and aft wheels. It's kind of small, but it's a small. Everything's kind of small on it. I did tighter turns so it fit in a smaller space. 56-inch inner rails. That's 1.4 meters. I did some banking in the turns, 30 degrees maximum. These are built in 10-foot sections, and they come apart just with a couple screws, and so you can transport it easy if you want to. It's really designed for flat ground, but custom frames could be made for any terrain. I decided I'm trying to minimize the number of wheels, and so it really just has 4 main wheels and 4 side wheels. Total drop is just under 1.4 meters, 4.5 feet. So yeah, it's pretty small. 50 feet total length, and a 12-foot wide planform. So the whole length of the coaster is 120 feet or something like that. And I decided to try my hand at a more decorative kind of cart. It needs a seat belt, anti-rollback feature on the lift hill, adult powered lift, no chain lift. And I'm thinking, yeah, it wouldn't be too hard to put a two train. Once you get the first cart working, the other carts are much easier because they don't have to have the fancy system on the front wheels. So, quick review of safety. Always store the cart away from the track so nobody can use it without an adult being there. Keep the kids away. Keep everybody but the kid who's riding it out away from the cart with a fence or safety tape. Seatbelt on there, attached to the steel frame. Provisions, so no hands and feet can get down in the wheels and the tracks. And then some kind of anti-rollback system on the lift hill. So this is the results of a spreadsheet that I use to predict the performance before I start building it. And kind of in a 2D CAD system, I kind of mapped it all out. And this is explained a lot better in a different video, so I won't go into it too much. But basically, it goes up a lift hill, down through a dip, all straight, up another little hill, and then down into a bank turn and a couple of turns out the end. But yeah, looked like it was going to have, as far as the results go here, no more than 2 Gs here in this first dip, and then a little bit of weightlessness, 0.75 Gs in the second hill, and then less than 2 Gs when it comes out of the second hill into the second dip. As far as banking around this 1.8 meter turn, the optimum turn angle 33 degrees down here in turn 5, and then this is kind of nondescript in here. It's kind of just generic. However, it turned out in here. It didn't really turn out this way, but just a 20 degree bend as an optimum turn angle there. So that's explained in another video a lot in more detail. So I think this is explained also. When you have a bank track angle, you have a radius to the inner rail, and depending on what bank angle, you can figure out with pretty simple trig what the radius of the outer rail needs to be given a certain track angle that you want. That's a simple formula. And I did a smaller radius than I'd ever done before with my hot forming process, hot sand forming, which is described in another video. And I went down to 56 inches inner radius there. So it's a smaller radius than I ever did before. That's just in the turns. So you combine these two radius pipes, PVC conduit, 1.5 inch inner diameter, and you get a bank turn. This is where the Ackerman steering is explained. This is part of a computer-aided design program that's free. I really would like to get a better program, but the good ones just cost a lot, $5,000 to $10,000, and this one's free. It's called FreeCAD, and it's difficult to use and crashes quite a bit, but that's what I used. So 70 inches between the rails. This is my cart, the four corners of it, kind of the center of the wheels. You can tell that when it's going around a turn like this, that the effective width is different. So you have a 5/16 of an inch, 8 millimeter difference there. And you could probably take that up just in tolerances, put the side wheels a little further out or something. But I decided to make my ties between the tracks a 1/4 inch smaller between the rails, so that this would hold on a little better. I don't know if that was necessary, but that's what I did, recognizing that the effective width of the track is smaller. I guess the effective width is larger in a turn, and so it's a 1/4 inch larger than the straight portions of the track. This is from the computer-aided design program, the cross-section of my tie. I have the cupped ends, and then there's a little flat part on the end of the cup so that I can maintain the distance between the rails very accurately. And so it's just to get the right dimensions of my wooden ties for a 14 inch center to center track gauge. This tells me exactly how long I should make my ties to end up with the right track gauge. This the 3D part of this FreeCAD computer design. Like I say, if I could get access, free access to CATIA or AutoCAD or Creo, the Pro Engineer, that would be much preferred. This is a difficult program to use, and anyway, but it worked well enough. It takes more time, but so I kind of went. This is my design work. You can design things up in a 3D CAD program and rotate it around and see what it's going to look like, and before you start building it. So it's a way of getting your design thoughts out. And a good designer is not, can be anybody. Design is kind of a skill set that is born of experience more than schooling. I think, you go to school, you learn engineering analysis and all these things, but until you get exposure to a lot of different designs, good design is really thinking about the load path. How do the loads are going to come up through the wheel, and they're going to come up through this little castor. It's going to come up here. It's going to beam over to the middle of this thing and then go up into the cart. So a good design is a lot of thought about where the loads are going, and what's the most efficient way to carry those loads and transfer those loads from the track to the person. So I go through a lot of iteration in design, and you can see engineers also like to keep track of their design. So I put this part number on here, BYRCc for cart, two-dimensional. I'm calling it a two-dimensional track because it separates the up-down camel hump things from the bank turns. They're not combined, and so it's really I'm still saying it's a two-dimensional track, opposed to my three-dimensional track, which is another subject. Dash 04, that's the fourth iteration of the track and cart. And then the 02, I obviously had an 01 that I didn't like. I didn't put it in this pitch. And then, so this is one where you can see how the members are stacking up here. I probably didn't like how close this crossbeam was getting to the track itself. And then I did an 03 where I kind of integrate this little cross piece and these little cantilevers that stick out to hold the wheel. One thing here is that, I realized at some point you don't have to just put the bolts and axles through the steel. Tubular steel is always a lot better than angles and I-beams. It's just more efficient and holds torque a lot better. But you don't have to put the shafts right through the middle. Just drilling a hole, that leaves a very small area for the shaft to interface with. But if you can also weld sleeves onto the sides of members, or you can drill a bigger hole and put the sleeve right through the member. So there's a lot of different ways to do this, and so this is a good way of thinking about those different ways virtually before you start building. You can see the different concepts for the side wheels. I decided I didn't need upstop wheels because I never go negative G's on this little coaster, so I just put a bar down there, and it never does touch. If you really shove this little cart hard, you would get some negative G's on that second hill, and these bars would rub against the bottom of the track and probably slow it down, which is a good thing. So you can see I got different concepts for how to support these shafts on the side wheels as it goes along. One thing to notice here is how whenever you're going to weld two parts together, it's good design practice to maximize the number of welds. Try to always do fillet welds, not butt welds. They're just much stronger. And so here I've maxed by cutting these H's into this hollow cross member here. I maximize the amount of welds. So I think that was a pretty good design decision there. So this is the kind of the full up 03 cart design. Imagine that there's two rails and that there's four of these subcomponents here, and then there's a whole more complex system on the back for letting this. Well, anyway, so you can see that's my final design. This is some preliminary work on making these little casters. You notice this worked out pretty well. You put this in a vise and get an angle grinder and a good face shield on. You can you can cut these out and then fit it all together. You'll notice this is like a weld fixture I made. We have a saying in engineering: good tooling makes good parts. And so if you have to make some special tooling to get these parts to fit up really well, then that's what you do. So here it is unwelded. The other note here is that, welding involves melting the steel 2,700 degrees. So there's a lot of thermal expansion and shrinkage that happens really quick. So if you weld all the welds on one side, then it's going to warp to that side. And so it's a good practice in welding to weld some on one side, turn it over, weld the other side, turn it back over, clean it up, weld a little more on one side, and then you get the kind of warping evens itself out from side to side. You don't end up with warped parts. It's just a good design practice. So anyway, that's kind of development of the little castors, the 4 of them that I needed. Here's kind of a fit up. I made my tightest curved track, and then I had this what I call a flying Ackerman searing fore and aft. This front set of wheels can roll from side to side 20 degrees to account for when it's going through a bank curve and doing transitions like that. The forward wheel assembly does not yaw, doesn't have to in this case. That's different than a bogie system. And I actually prefer the bogie system, so I don't expect that if you want, I do bogie on everything from here on out. But it was an interesting experiment to try this Ackerman, and it worked really well. Cart really doesn't want to go backwards because these bogies kind of tilt to the side and kind of lock it onto the track. So that's another good thing. It doesn't really want to go backwards very well. These white wheels are just temporary. You can see there's too big of a gap between the side wheel, and the track. And I had larger wheels on order at that time. So I ended up, I thought I probably needed some kind of a limiting system to limit the angle that the castors can turn. And it turned out that as I beefed up this cantilevered side wheel structure here, got kind of ugly, but it limits the amount the wheels can turn to the side. But that's kind of the design I ended up with. So here's the finished frame of the cart with the 4 bogies on it. I guess the upstop bars aren't on there yet, but I just welded them to the top of those bolts. Anyway, don't look at my welds. They're pretty ugly, but they seem to work. So here's going from the design out to the shop to make the track. I developed a little spreadsheet that told me the arc length of each of these pieces, going from the little beginning radius up the hill. It's only a 26-degree slope, which really makes it easy to push the kid in the cart up the slope. And it's not too high, so that worked out really well. All the radii on the up-down portion of the track are this 69 3/4 inches. And then I just developed a spreadsheet that told me what the arc length was. So once I had all the pipes formed, it was easy to make the track pieces and then start putting the whole thing together in my garage. So here's my forming session. Lots of pipes lined up. Here's the cradle I use, and this is covered in another video too. I put hot sand in the top of this and shake it a bit, and it rolls down. Takes a couple minutes. Here, as you can see, my table saw is set up for putting the little cups on the end of the cup shape on the end of the ties, which I've talked about in other videos, why I like that system. So I'm kind of going from one to the other, making ties. You have to make a lot of ties, and so as the sand is heating up in my oven inside the house, I'm making more ties as the day goes along. Here's my forms on the wall. There's 4 different radii on this wall. You just put the sand in, let it heat up a little bit, run it over and stick it on a form, and it just droops down, and half hour later you pour the sand out, you got this really nice curved pipe. So here's a whole stack of pipes here, and it's kind of a staging area for building the track pieces, for letting the ties dry. I dip them in fence and deck stain so that the ends are very well coated. This is where I should have painted the formed PVC conduit for ultraviolet protection. I did end up putting Aerospace 303 on it, but I think paint's a lot better way to go here. So I should have, if I had to do over, I would paint the PVC at this point before it had any exposure to sunlight. Sunlight embrittles the PVC. I'm not sure, the PVC conduit has sunlight inhibitors in it. It's supposed to be better, but I don't know how much better. I don't have much data on that. So I'm just, anyway, this is what my garage looks like when I'm building these things. This is the lift hill here, hooks on, goes over the first hill, goes around. This is really the funnest part. You just start sticking this together, and you do need some expertise in. I don't ever want to put posts and cement in my yard, and so I've developed this kind of A-frame system of supports for the track, and they really do get stiff. I really like this system. It's just made with 2x4s. 2x4s in the United States, 2x4s cost $2.50 each. 8-foot 2x4, so you can just use a lot of them, and it really makes your track stiff, and really makes it easy to support everything well. So here's the track, putting it up outside. It wasn't a totally flat piece of ground. Down here on this end, down at the far end, I had to kind of remake the struts. You do need some expertise in places like this for doing compound cuts on the boards, and that helps a lot. But not too much on this track. You do have to have some compound cuts here where this interfaces, and the better job you do there, the better it fits together. So I tried the little card out, and the Ackerman steering seems to be fine. This is my third coaster. It only took maybe 2.5 weeks from design to finish for the track and the cart. I'm thinking somebody could rent this thing out. It's easy to separate, put on a truck, and take to someone's yard. Some rich kid could have a nice birthday party or something. So this is my nephew Keaton, 3 years old. He weighs about 30 pounds, and he was zooming around this thing, having a good time. So I didn't have all the supports on it yet, but just for trying it out, he was having a good time. You can see at the time I had not the fancy cart, but I just put a storage bucket on there with some Gorilla Tape around it to reinforce it, and just to give it a try out. I do have a little seat belt in there on him, kind of rigged in there, and looked like this thing was really tracking smooth, very little noise on it, and very smooth. You do notice that my fastener heads don't interfere with any of the wheels. They're up at an angle here where they won't interfere with the main wheels or the side wheels, so there's a lot less noise. This is my anti-rollback provision. It's just a bungee cord on 2 boards where the cart can go over it one way but can't go back the other way. That's so that if I slip and fall, the cart doesn't go back into this non-banked turn and maybe cause a problem. So there's the anti-rollback device. This is just some detail about the final framing. You can see I put diagonals in here to make everything really stiff. Every tie is supported one way or another, hopefully toward the center of the tie. And when it gets flat, it's pretty easy to do. Just these are 3.5-inch galvanized screws holding the whole thing together. And it's very stiff, very portable, very efficient, I think. Everything covered with, all the wood covered with fence and deck stain. So here's the results. I have an accelerometer app on my smartphone and duct taped it to the floor in the cart. And these are the XYZ, as coordinate system of the cart being X is forward, Y is sideways, and Z is up and down. This is where I just, and you do have to filter out some data for accelerations here. A lot of times this is a real science to do this properly. But because some accelerations are very small and really don't count. Really, the only accelerations you're worried about in this kind of an application is accelerations that are longer than 200 milliseconds. And so you do have to filter some data out that's not really what a person would feel, because 200 a fifth of a second, anything shorter than that, you don't really have time to react. Your body, the mass, doesn't have time to react to that. So anyway, that's another subject, but this is kind of what I call a soft start, where you just kind of let the cart go over the hill by itself. And it worked out really well, because what I'd predicted is just around 2 Gs, and that's what it does. This is in meters per second squared over here, so you convert to Gs and then add gravity, and yeah, 1 G from going through the first dip, and another G for gravity. And then when you come back into the second hill, you go a little negative on the centripetal G's, which subtract from the gravity 1 G, and you get 0.6. I think I predicted 0.75 G's. So a little bit of weightlessness on that, just enough to make them feel fine. Now this is what I call a hard push. I just really shoved the cart hard at the top of the lift hill, and of course you get some bigger G's. And if you had a kid that really wanted to have thought it was a little too benign, you can just give them a hard shove and get up to 2.6 G's, and actually go negative G's on the second hill. You'd feel lifted out of the cart a little bit, quite a bit actually. And so you want to be really careful if you're going to push this. If I'm going to push this cart, I just let them go around and have a good time. So then I started working on some kind of a theme for this thing. I call it the Little Rocket. I found this, I had this water barrel, 15-gallon water barrel. I think it cost about $20. And I actually tried to form the end of the barrel into a nose cone shape by heating it with a torch and pressurizing the barrel, but that didn't work at all. And it just develops leaks and stuff. So I cut out the front of the barrel and found this green bowl at a thrift store for $1, and just a funnel, and attached that to the front. Put some split insulation around so that around the opening, and found some cheap flower pots for the nozzles. I did, with the extra plastic that came out of this cutout, I flattened it with heat. And then I kind of did a tab and slot attachment here. I don't have a real detailed picture of that, but imagine just putting slots in here and tabs, and then going inside and heating up the inside of the tab and poking it over with a hot knife. And that worked really well. Analysis seemed good. I did some heavy testing. I put 66 pounds in there and ran it around, so it's qualified for 30 pounds with a 1.5 factor safety. All safety and certifications covered in another video. So, but I did go through a process. When I put the blue rocket cart on here, it lifted up the center of gravity about 2 inches, and so that makes it, when it goes through this turn here, it kind of, there's more drag to it or something. So I'm limiting the size of kid that can go in there. It's limited because the kid can't get in there anyway. I also put a little kind of a control knob in there, just a plastic toy that makes noise. It makes rocket noises, and they can push it back and forth and make these noises. I think it's really cool. Total cost with the cart and all the track and everything, about $450. I worked about 50 hours on it. It was a 2.5 weeks from start of the design to the finish of the track, with the forming and everything. And then you can see a few videos of different kids riding in the blue cart on my YouTube channel. So everything seemed to work as predicted. Ackerman seemed fine. I probably go with the bogie system on the next one if I do another one. But the Ackerman seemed to work fine. And that's it. Thanks for watching.